Towards the end of the last chapter, we started to look at some reactions we could do with aromatic compounds. Now, we noticed that it's really difficult to do reactions on the benzene ring itself, so instead we started looking at reactions at the benzylic position, for example, and things just off of our aromatic rings. In this chapter, we are going to look at reactions on our benzene ring, specifically what we call aromatic substitution reactions, where we substitute one of the hydrogens on our benzene ring with some other functional group. All right, so just to reiterate, while you would normally expect an alkene to be relatively reactive, and even though a benzene ring has 3 carbon-carbon double bonds, we don't see the kind of reactivity that we normally would expect. So, for example, one of the standard tests for an alkene is to add bromine to it, and you'll notice that reddish-brown color of bromine disappearing really rapidly. All right, that's usually a very quick, easy test for the presence of an alkene. Despite the fact that benzene has 3 carbon-carbon double bonds, there's actually no reaction with bromine. We don't see that same addition product that we would normally see with cyclohexene, for example. All right, so the reason for this, of course, as we saw in the last chapter, is the unusual stability of these aromatic systems. Right? They really want to stay in those aromatic as those aromatic rings, and doing that addition reaction across one of those double bonds would take that ring out of that stability. Okay, and that's why it's just not energetically favorable. Okay. So while we can't do a halogenation reaction, we can make the dibromo product across one of the double bonds, if we add in some iron, we can swap out one of the hydrogens on our benzene for a bromine. Okay, so please note that the reaction on the top there, where we add bromine, a bromine molecule across the double bond to make that dibromo product, that's an addition reaction, right? We're adding across a double bond. But notice that in the reaction with using iron, we still have our benzene ring, right? We still have our conjugated pi system around those 6 carbon atoms in the ring of our benzene. Notice that the hydrogen that's not shown is swapped out for 1 bromine atom. Okay, so please keep in mind that this is a substitution reaction. All right, so we're substituting the hydrogen for a bromine. Okay, now that being said, even though I use the word substitution, you can already tell it's probably not going to be your typical SN1 or SN2 mechanism. We've already seen back in the chapter last semester on substitution reactions that sp2 hybridized carbons aren't really good for forming carbocations. Okay, so it's not going to be your typical substitution. Anyway, this type of reaction is what we're going to look at in this chapter. This is what we call an electrophilic aromatic substitution, or EAS reaction. All right, so in all of these examples, we're going to swap out a hydrogen on our benzene ring for some other group. We just saw an example with a bromine. We can swap it out for a chlorine, for a nitro group, for a sulfate group, for an alkyl group, or even a ketone group. All right, so keep in mind that these aromatic rings with their 3 pi bonds in amongst 6 carbons are very electron rich. All right, so basically that ring is going to act as a nucleophile, right? So you have things that are going to attack that benzene that are going to be electrophilic. They're going to seek out that extra electron density on your benzene ring, hence electrophilic aromatic substitution. All right, so how does iron help this reaction happen? Well, so first of all, the iron reacts with bromine to make iron 3 bromide. All right, so we have this iron bromine complex, which then picks up an extra bromine molecule, right? Now, when it does this, it actually gets a bromonium ion to break off and create this iron-bromine complex over here, this iron tetrabromide complex. So we have a positively charged bromine ion, or a bromonium cation. Now, since this has a positive charge, this is going to be electrophilic. Okay, again, hence the name, right? We want something electrophilic to seek out that electron-rich benzene ring. All right, so that's kind of what happens basically. So that your benzene basically does a nucleophilic attack and picks up that bromonium ion, and in doing so now, it makes what we call a sigma complex. So we have a positive charge. We have a carbocation here, and it's going to be resonance stabilized by that ring. So we have this double bond moving over here, which would shift the positive charge over here. We could then have this double bond move over and basically have that positive charge shift around the ring accordingly. All right, so even though we have a carbocation here, that carbocation is resonance stabilized, and so this sigma complex is a pretty stable pretty stable intermediate. Oh, a quick note here about iron bromide. We can also use aluminium bromide too sometimes. All right, so here's a picture of of our sigma complex, and you can see again how that resonance stabilization spreads that positive charge around the ring, and therefore makes that sigma complex relatively stable. Here's a picture of the hybrid structure showing how that positive charge is partially spread out throughout the whole ring. Okay, so what do we do to make the stable product? Well, notice that now this carbon over here, which is sp3 hybridized, can just have a proton transfer occur, and you basically restore aromaticity to the ring. Okay, so again, this intermediate, while it's resonance stabilized, is still an intermediate, not super stable. It'll go towards this more stable product relatively quickly and easily. Okay, and so you lose HBr as a byproduct, basically. Right, so that extra bromine that was on your iron center picks up that proton and leaves as HBr. Notice that you restore your iron 3 bromide. So basically, iron 3 bromide is a catalyst here. Okay. So here's the energy profile of of the mechanism. All right, so you can see how basically by restoring aromaticity, this product is very thermodynamically stable. Okay, it makes way more sense to have this product form than this addition product, right? So notice that since your addition product takes your molecule out of aromaticity, the potential energy of that product is way higher than the original reactant. All right, so so definitely that's a very endothermic reaction. All right. So I mentioned earlier that in addition to a bromo product, we can also make a chloro product. So if we use aluminium chloride instead of iron 3 bromide and chlorine instead of bromine, we can swap out a chlorine atom for our hydrogen. Again, very similar mechanism as we just saw with bromine. Of course, instead we have chlorines instead of bromines, and we have an aluminium center instead of an iron center. All right, and and then we get the chloro substituted product, and HCl is a byproduct, and of course, the aluminium chloride is catalytic here. All right. So regarding the other halogens, fluorine and iodine aren't really practical for this kind of substitution reaction for opposite reasons. Fluorine is just, that reaction just happens a little too violently to make it very controllable and very practical. And with iodine, it's generally too slow and too low yielding. Okay. So again, if you want to see that whole mechanism, note the similarities here between our aluminium chloride reaction with chlorine as compared to the iron 3 bromide and bromine reaction we saw previously. So again, you form a complex with your aluminium, and your benzene picks up that partially positively charged chlorine, And it basically forms that sigma complex, which, as we see again, is resonance stabilized. And of course, then that complex can then pluck off a proton from that same carbon, thus restoring aromaticity. Next up, we have sulfonation. So here we take our benzene reacted with what's called fuming sulfuric acid, which is basically sulfuric acid mixed with sulfur trioxide. And we get this sulfonic acid group here. I may have accidentally referred to this as sulfonate in an earlier slide. Just a quick note here. When this is protonated, it's called a sulfonic acid. When it's deprotonated, so we have an ion here, then it's the sulfonate ion. Okay, so, but anyway, here we have a sulfonic acid. All right, now how does this work? Again, we need a really strong electrophile here to attack our benzene ring, or have our benzene ring do a nucleophilic attack to it. And here our electrophile is sulfur trioxide. We have our big squishy sulfur in the middle, and it has 3 oxygens double bonded to it, very electronegative oxygens that are sucking electron density away from that sulfur, and so that allows that, that kind of deprives that sulfur of some electron density. Okay. The other thing that's really useful here is that because sulfur and oxygen are from different periods, their p orbitals, their unhybridized p orbitals when they're sp2 hybridized, are not the same type of p orbitals. We're talking about 2p in oxygen versus 3p in sulfur. So we have different sized p orbitals, and therefore they don't overlap perfectly. So even though you have a lateral overlap forming those pi bonds, it's not the best lateral overlap. All right, so basically, instead of having a good, strong double bond between that sulfur and oxygen, it kind of has more of a single bond character to it. And as such, if you look at the formal charges involved there, again, remember, those oxygens are more electronegative. So we've got close to a formal charge on that sulfur, okay, instead of it having a nice complete double bond on it. Okay, so having that partial positive charge on there allows, again, a nucleophilic attack from that benzene ring. Okay, just like we saw in our previous example with halogenations. All right, so again, we have our, we can draw a curly arrow going from our double bond to that sulfur, and here we can see the sigma complex that's formed accordingly. Okay, so we have a sulfonate group attached to our sigma complex, and again, this is resonance stabilized. This is going to be stable, a pretty stable carbocation because of that resonance stabilization that we saw earlier. Okay, so again, here are all the resonance structures, and here's that hybrid showing that. All right, and then as before, you can have some base come along, pluck off that proton, restore aromaticity. Notice that the product you have here is your sulfonate group. So if you protonate that, then you get the corresponding sulfonic acid. Okay. Protonating it isn't a problem. Keep in mind, this is being done in the presence of sulfuric acid. You have a pretty acidic solution. This is going to be driven towards that protonated product. All right, so that actually is what drives this reaction towards your product. It actually turns out that if you use dilute sulfuric acid, the equilibrium is kind of shifted back towards the original benzene reactant. So having the concentrated fuming sulfuric acid is what drives us towards that sulfonic acid product. Okay. Consider the reversibility of this product, of this reaction. We're going to take advantage of that later on in this chapter. It's going to come in handy from a synthetic standpoint when we start looking at protecting groups. All right, anyway, more on that later on in this chapter. All right, next up we have nitration. So here we're adding on a nitro group that's just an NO2 group. The reagents we're going to use here are concentrated nitric and sulfuric acid. All right, so our sulfuric acid here is a proton source, and it converts our nitric acid into the nitronium ion. All right, so basically we protonate the OH group on our nitric acid. It leaves as a water molecule, and you are left with this nitronium ion. And notice the similarities between our nitronium and our sulfur trioxide in the previous example with sulfonation. Notice that we again have an atom here in the middle connected to oxygens, and therefore you have these electronegative oxygens pulling electron density away from the central atom. In the case of the nitrogen here, of course, we do have a formal positive charge, so that definitely helps. This is positively charged. This is going to really readily seek that electron-rich benzene ring. All right, so again, very similar mechanism. You're probably seeing a pattern here, right? We have our arrow going from one of our double bonds to that nitrogen. We form our sigma complex, which again is going to be resonance stabilized. That's why this is a good intermediate. All right, again, showing what that stabilization looks like. And then, of course, you have a base come along and pluck off a proton, restoring aromaticity, and there's your nice neutral product. Okay, now the nitro group from a synthetic standpoint is pretty useful. All right, where we're going to, obviously there are molecules, products out there that where we want to have a nitro group, but one extra synthetic utility here is that we can convert a nitro group into an amine. We can basically do a reduction using either iron or zinc and hydrochloric acid, and our nitro group gets converted into an amino group pretty well, actually. Okay, so that's something to keep in mind for any synthetic problems that require you to tack on an amine to your benzene ring. Realize that you can do so in two steps. In your first step, make your nitro benzene using concentrated nitric and sulfuric acid, and in the next step, use either zinc or iron and HCl, and you will reduce that to the corresponding amine. In the previous chapter, we looked at some reactions at the benzylic position on, on a benzene ring with an alkyl substituent, but we didn't actually see how we added those alkyl substituents in the first place. And I think I may have alluded back then to the Friedel-Crafts alkylation reaction. So basically, we are doing. You could kind of think of this as a nucleophilic substitution on an alkyl halide, which we've already seen last semester in your typical nucleophilic substitution reactions. That being said, in this sense, I don't think the alkyl halide's a strong enough electrophile to encourage this EAS reaction. And so you have to kind of encourage it by introducing a catalyst. And in this case, the catalyst that we use is actually a Lewis acid. All right, so we're going to use aluminium chloride in addition to our alkyl halide, and that helps sort of prime our alkyl halide for this substitution reaction. Okay, so basically what happens is our the halogen on our alkyl halide attaches to our aluminium center and our aluminium chloride, okay, which essentially sort of plucks off that halogen, making our aluminium complex here and a carbocation. Now, we have a formal positive charge on that carbon, and therefore this is going to be much, much more effective for our EAS reaction, right? This is going to be a much stronger electrophile, rather than just having the partial positive charge that we would have had just from that chlorine alone. Okay, so of course this then attacks our ring, or the ring attacks that, I guess, if you draw the arrow going that way. And you have a sigma complex again, just like before. Okay, so now that being said, you've got to be careful about the types of alkyl halides that you want to make here. I don't know if you noticed in that last example, but that was a secondary alkyl halide that we used. All right. What happens if you use a primary alkyl halide? Well, you're not going to go through a primary carbocation intermediate. The reason for this is that that carbocation is going to undergo a rearrangement, which will then produce a secondary carbocation, or tertiary, depending on the shape of it, and therefore that's going to be your major product. That secondary carbocation is more stable and therefore will yield your major product. Okay, so if you're trying to get the a primary alkyl substituent here, you can't do it directly under Friedel-Crafts conditions. All right, so there is a way to do it, and we'll get to it in a second. But understand that when you're planning out these types of syntheses, watch out for this pitfall. This is a common wrong answer you're going to see on multiple choice questions. So it's, just be ready for that type of question is what I'm getting at. Okay, so basically, you can see here that we have, instead of breaking off and forming that primary carbocation, you can see even in that coordinated step with our Lewis acid complex, we can have our hydride shift right there itself to make the more stable secondary carbocation. Okay. All right. So here's the full mechanism showing how it yields that major product. Again, it's the same as before. You have your benzene, attacking that carbocation. You make your sigma complex, your aluminum complex comes along and plucks off that proton. It acts as that base there to pluck off that proton, restoring aromaticity and your product. But the key thing here again is that even though you started off with a primary alkyl halide, you wind up with a secondary, alkyl substituent because of that rearrangement, because of that hydride shift. So watch out for that. Okay, so the other thing to watch out for Friedel-Crafts alkylation, of course, is that your Lewis acid complex, your alkyl halide and Lewis acid complex, can be attacked directly from the ring. You don't actually have to break off your carbocation first. We kind of saw this in our previous examples with with halogenation. I think when I first introduced the idea of using iron 3 bromide and bromine to put a bromine, to substitute a bromine on your benzene, I initially said that we could use, we make a bromonium ion, but the subsequent mechanisms showed that it was actually the, your benzene actually attacked the bromine while it was still attached to your iron complex, right? So in the same way here, our benzene can directly attack our Lewis acid complex. Okay, so something to watch out for there. Okay, so here's what that mechanism looks like when you have it directly attacking that the site where that chlorine's attached. Okay, of course you can see here that when that happens, of course there we get that primary product. Though keep in mind that this is the minor product that we make. Okay, this is it's more likely to have that that secondary products going through a lower energy transition state. So that's definitely going to be the major product. Okay, all right. So yeah, so basically the other reason, from a sort of collision theory standpoint, if you're trying to understand why is that secondary product the major product, keep in mind that you do need a collision between your benzene ring and your complex to have that primary product form. So in the meantime, though, that hydride shift is intramolecular, right? It's happening, the pieces are right there, all in that complex. So it more readily forms that secondary intermediate. Okay, and so that's probably going to form before a benzene ring collides with that complex to make the primary product. Okay, so that's a major limitation to Friedel-Crafts, and it's definitely not the only one. So let's look at Friedel-Crafts alkylation and take into account what are the things we need to consider when we are relying on a Friedel-Crafts alkylation. Okay. First of all, you need your leaving group. Your halogen has to be attached to an sp3 hybridized carbon. Okay, we saw this back actually in back in the chapter on substitution reactions, way back in in the first semester. Your leaving group is going to have trouble leaving an sp2 or sp3 hybridized carbon because that's just not very stable, not very good at stabilizing that cation as a result. Okay, definitely not at that directly on that sp2 carbon, right? If you had the chlorine over here and you had an allelic carbocation, that'd be fine. In fact, that would be great. But here, your chlorine is attached directly to that sp2 carbon. That's not going to leave very easily. Same thing over here. Here we have a chlorine directly attached to our benzene. Again, that's our sp2 carbon. This is not good. You're not going to break that bond and leave behind a carbocation here, right? This would lose aromaticity. It would be very difficult to do that. So in both these cases, we do not see a reaction. So your alkyl halide has to have the chlorine on an sp3 hybridized carbon. The other thing to watch out for, it's often difficult to stop this at just one substitution. All right, we're going to see later on that alkyl groups are activating groups. As such, they kind of activate that benzene ring. They push electron density into that benzene ring, making it more nucleophilic, and therefore polyalkylation oftentimes can occur. And so this is something, again, you have to consider when designing a synthesis with Friedel-Crafts alkylation. And we'll look at this later on in this chapter. We'll see ways we can kind of control this. And then finally, the other thing to look at is actually the opposite. If you have a deactivating group on your benzene ring, basically it might not be reactive enough to occur. Even with your Lewis acid catalyst, you still need an electron-rich ring to act as your nucleophile in this situation. All right, so if you have a deactivating group that sort of sucks electron density away from that ring, you're not going to have a Friedel-Crafts alkylation occur. Okay, and again, we'll talk more about activating and deactivating groups later on in this chapter. Now, in addition to Friedel-Crafts alkylation, we can also do what's called a Friedel-Crafts acylation. So essentially, we have an acyl group is basically a ketone or a carbonyl with a, basically it's attached to our benzene ring from that carbonyl. Okay, so again, very similar to a ketone in that you have these two carbons attached to your carbonyl carbon, but again, specifically when we have a carbonyl with an R group attached to it, we refer to that as an acyl group. Okay, the difference here, of course, we're still using a Lewis acid, but instead of an alkyl halide, we're going to use an acyl halide, or an acid chloride, as it's also known. Okay, so instead of our our alkyl group attached to our chlorine leaving group, we have our acyl group here. Okay, so instead of going through a carbocation, we use what's called an acylium ion. So it's essentially your acyl group converted into a cation. So much in the same way, your Lewis acid, your aluminium center in your Lewis acid picks up your chlorine and forms this complex here. If you cleave that carbon-chlorine bond, of course, there's your acylium ion. And once again, you have that formal positive charge, which makes this a pretty good electrophile. All right, something to keep in mind here, the acylium ion is resonance stabilized. Again, that kind of helps with the stability of that intermediate, right? And it helps that, makes it stay, helps it last long enough to react with your benzene, basically. So as before, we have a very similar mechanism. Again, you have your electrophile here, your acylium ion as your electrophile. So your benzene ring attacks that, forms that sigma complex, which as always is resonance stabilized and therefore much more stable. Your aluminum complex acts as a base here, plucks off that proton, restores aromaticity, and there's your product. Okay, and of course your aluminium chloride is regenerated and so therefore it's behaving catalytically. All right, so coming back to that earlier problem that we ran into with Friedel-Crafts alkylation, remember, we can't use a primary alkyl halide because it's going to rearrange. We're going to get the secondary or tertiary rearrangement due to a hydride shift that occurs. So how do we get primary alkyl groups on a benzene ring? And the answer is actually to go through a acyl intermediate, right? So we saw that acylium ion doesn't rearrange, which is great. So we can do our Friedel-Crafts acylation and then reduce that resulting acyl group, the carbonyl in our acyl group, back down to an alkyl group. So we do this through what's called a Clemmensen reduction. Essentially, we use amalgamated zinc, so it's zinc that's kind of dissolved in mercury, and reacted with hydrochloric acid and heated up, and that gets rid of the carbonyl. It reduces it down to just a regular sp3 hybridized carbon, to your regular methylene carbon, and you've got your alkyl halide. And notice that your alkyl group here is a primary alkyl group. Okay. Another thing to realize with the Friedel-Crafts acylation versus the alkylation is that acylation does not involve polysubstitution. We'll see later on that acyl groups are deactivating, unlike alkyl groups which are activating, and therefore the acyl group kind of makes that benzene ring a little bit less electron rich, and therefore it's not going to want to keep on undergoing Friedel-Crafts reactions. Okay, so we've talked a bit about activating and deactivating groups. Let's go and examine that in more detail. Okay, what does it mean for a group to be activating versus deactivating? As the name implies, an activating group makes our benzene more active and more reactive. For example, if we look at toluene, which is just methylbenzene, we'll notice that it undergoes nitration much faster than plain old benzene. All right, so why is that? Well, the methyl group on our toluene activates our benzene ring. We've seen before that alkyl groups kind of push electron density away towards whatever they're bonded to, right? We saw this way back when we looked at carbocations back in substitution reactions, right? If you have more alkyl groups attached to your carbocation carbon, so if you have a tertiary carbocation, for example, it's much more stable than a primary one because those alkyl groups are pushing electron density and sort of stabilizing that carbocation. They're kind of like counteracting it a little bit, right? They're balancing it in a way. Okay, we call that hyperconjugation. It's the carbon-hydrogen bonds in your alkyl group that overlap with that MTP orbital on your carbocation, right? So in much a similar way, we still have a hyperconjugation here where those carbon-hydrogen bonds kind of overlap with the p orbitals on our in our conjugated pi system of our benzene ring. Okay, and so as a result, are able to kind of push electron density towards that benzene ring. In addition to making our reactions happen faster, these activating groups, also control the regiochemistry, the regioselectivity of where other substituents, the incoming substituents go. All right, so for example, I pointed out that, in toluene, that methyl group is an activating group, right? It's like all alkyl groups, it's activating. Now, if we do a nitration reaction, where's that nitro group going to show up on our benzene ring? Is it going to be at the ortho position, the meta position, or the para position? Well, it turns out that it selectively prefers the ortho and para positions, but not the meta position, right? And why is that? Okay. Well, to understand this, we've got to look back at that sigma complex and also look at the resonance structures associated with it. All right, so if we look at our if we have our nitro group attacking at the ortho position, for example, notice that the sigma complex involves a positive formal charge on that carbon that the methyl group is attached to, right? And as I pointed out earlier, alkyl groups stabilize carbocations. They push electron density towards that MTP orbital through hyperconjugation and make that a more stable complex. Okay, so it makes sense that the activation energy for this sigma complex is going to be lower in energy and therefore much more favorable. What about for meta and para position? So if we have our nitronium ion add-on at the para position, notice that we also wind up with an intermediate, one of our resonance structures where that positive formal charge is on the carbon that our alkyl group is attached to. And again, we have that stabilization from that hyperconjugation off that alkyl group. It's going to push electron density towards that carbocation and therefore lower the potential energy of this sigma complex, and therefore, you're going to need less activation energy to get this reaction going towards that product. What about the meta one, though? If you notice, if we look at the resonance structures for the nitronium ion adding at the meta position, notice that the positive charge on our sigma complex skips over that carbon with the alkyl group attached to it. As a result, this is not going to be lower in energy. It's going to be at the same energy as you'd expect, okay, for like any sigma complex. So, what this means, though, of course, then, is that since the activation energy is lower for those other two sigma complexes, that's basically giving it a kinetic pathway. We're going to make that kinetic product by going through that lower activation energy. We're going to make more of that product faster. In addition to alkyl groups, which are activating through hyperconjugation, alkoxy groups are also activating groups, and they activate the benzene ring through induction. All right, so basically the lone pair on your oxygen pushes electron density into your ring through resonance structures. As you can see here, basically these electrons can't swing towards the alkyl part of the alkoxy group because that would involve a Texas carbon. You'd have 5 bonds to your carbon, so obviously they can't go that way. But we can have them swing down this way and get involved in multiple resonance structures, as you can see here. And you can see that resulting Zwitter ion, or the negative charge of the Zwitter ion, is pushed around your benzene ring and therefore is resonance stabilized. Okay, so your methoxy group in this example is even more activating than your typical alkyl group. So as a result, you can activate the groups. Sometimes that can be a bad thing synthetically, in that you encourage polysubstitution. Right, your ring is so active that it undergoes your reaction even more than you might want. So you can see here that we have a polysubstitution where we don't just add one bromine, but we actually added both ortho positions and the para position. Okay. Notice again that just like our methyl group earlier, like alkyl groups, the methoxy group is still an ortho para director. Okay, so our new substituent comes in selectively at those ortho and para positions, but not the meta position. And you can kind of, if I go back a slide, you can kind of see also like how that that negative charge on your carbocation is kind of pushed around selectively to those ortho and para positions, but not the meta position. They kind of skip over the meta positions, and that's why those sigma complexes are not favored. They're not stabilized. So here are those resonance structures for the different sigma complexes we can form by having our new substituent at various positions. And again, notice with those ortho and para substituents that we have an extra resonance structure due to the involvement of those lone pairs on that oxygen, and so we have more resonance stabilization, and we don't have that available in with our new group at the meta position. Notice again that the sigma complex kind of skips over the carbon with our where our methoxy group is attached to our benzene ring, and therefore those lone pairs in that oxygen can't get involved. Okay, so just like before with our methyl group, again, notice how much the difference in activation energy. It's not that like the complex with the meta positioned group is raised in activation energy, but it's more that the activation energy of the ortho and para ones are lowered, and that's what drives the reaction towards those products. Okay. Oh, quick point here about the para product. Notice that again, the activation energy is even lower for that para product as opposed to the ortho one, due to steric hindrance from this alkoxy group. You still have this alkyl group that's sticking out here. It is better to have the your incoming substituent at the para position because there's less steric hindrance there. Okay, so in general, as I pointed out, all activating groups are ortho-para-directos. All right, so that's something to keep in mind when you're designing syntheses, or when you're just trying to figure out how you get from reactant A to product B. So with that in mind, let's practice this. So here we're starting off with a benzene ring, and we want to wind up with this di-substituted product. Okay, so notice that we have a nitro group here, we have an alkyl group here, and I'll point out it's a primary alkyl group. That might be a hint as to what's going on here. So ask yourself what order, what reagents do you use, and what order do you use them in? Okay, because you'll find that the order in which you put in your substituents might be important here because of those directing effects. Okay, and we'll practice that some more, but pause the video here and go ahead and see if you can figure out this one before I show you the answer slide. Okay, so if you're back after having paused this video and taken a crack at this problem, let's look at the answer. Okay, so I went out of my way to point out that this was an primary alkyl group. And so that should have hopefully raised a red flag in your head that you can't just do a simple alkyl Friedel-Crafts alkylation, because of course you can't add a primary substituent that way, right? It's it would rearrange, especially given this kind of alkyl group and the fact that we've got a tertiary site right here. It would rearrange to give you the tert-butyl group on here instead. So you actually have to do an acylation and then reduce it accordingly, okay, to get that alkyl group. Now, notice that we're also adding on a nitro group. Okay, now the order in which we do this is very important because we want the nitro group and the alkyl group to be para to each other. Well, we know that this alkyl group is ortho-para directing. All right, so it's very important that we have that alkyl group in place before we try to add on the nitro group. Now, the other thing to consider is, does it matter whether we do our nitration before or after converting our acyl group into the alkyl group? And the answer is yes, right? Our acyl group, I think I may have pointed out earlier, is also a deactivating group, just like the nitro group. So neither the acyl group nor a nitro group would be useful for getting our two substituents here to wind up being para to each other. So it's very important that we first do our acylation and then reduce it, do our Clemmensen reduction to an alkyl group, and only then proceed to adding on our nitro group. All right, so that's a nice segue into our deactivating groups, right? I just mentioned that our acyl groups and our nitro groups are deactivating. What ramifications do deactivating groups have on our benzene ring and our synthetic methods? Okay, well, again, just as activating groups push electron density into your benzene ring, deactivating groups suck it away. They pull electron density away from your benzene ring and therefore make that ring less electron rich. All right, and hence the name deactivating. So the way this influences our transition states is kind of a little bit backwards from activating groups. Instead of making certain transition states more stable and therefore lower the potential energy, instead what's going to happen here is that our transition states are actually going to increase in energy. All right, so later on when we start looking at the selectivity of a lot of these deactivating groups, it's due to this opposite effect. It's because the products that don't form are made less stable, or their transition states are made less stable, rather than the products that are formed, through more stable transition states, like with the activating groups that we just saw. All right, so let's see an example here. So if we have a nitro group in place and we look at another substituent adding on, again, if we look at the, at our sigma complexes, notice that with an ortho group, or with a substituent coming in that ortho position, we have a positive formal charge on that carbon that our nitro group is attached to. And with a para position one, we again wind up with that positive charge on that carbon that the nitro group's attached to. In both those cases, remember, our nitro group's going to be sucking away electron density. That's going to destabilize that carbocation, right? It's already positive. You're pulling electron density away from something that's already positive, right? That's going to increase that potential energy, right? It's going to increase the activation energy for that transition state. Okay, the meta, with the meta position, that sigma complex skips over that issue, right? You still have a, it's still got a relatively high activation energy, but it's not, as high as these sigma complexes if you have the substituent coming on at the ortho or para position. Okay, and so essentially the meta attack here is just not as bad as the other ones. Okay, and that's why deactivating groups tend to favor meta attack. Okay, and you can see here, in contrast this with the activating groups, it's not so much that the ortho, that the meta position is lowered in activation energy. It's just more that the ortho and para ones are raised in activation energy and made less favorable. All right, so we've seen so far that if you have an activating group, it tends to be ortho and para directing. The new substituent coming in comes in either at the ortho position or the para position, sometimes more selectively for the para position, depending on how bulky that activating group is. Okay, with a deactivating group, we see that generally it's going to go to the meta position, right? And probably with a lower reaction rate and lower yield than we would see with activating groups due to the loss of that benzene ring becoming less electron rich. Halogens are the exception to this. They're pretty electronegative, and so therefore withdraw electrons through induction. So they're still like sucking away electron density from your benzene ring and deactivating that ring. However, they have lone pairs on them that don't really have anywhere else to go, and so therefore through resonance can be used to stabilize a transition state. And therefore, as we've seen with ortho and para groups, there's a transition state where that gets added when we have these inductive effects, when those lone pairs on that group, on that atom next to the ring, gets involved. So we saw that earlier with our methoxy group. It's going to be similar resonance structures here with a halogen. Okay, so here again, notice that in the case of our ortho and para positioned groups, substituents coming in, notice that we have an extra resonance structure in our sigma complex, and therefore it's more resonance stabilized. With the meta position, we do not have that extra resonance structure. It kind of skips over that position. The lone pairs on that chlorine can get involved, and therefore this does not have that extra resonance stabilization. So to kind of put this into perspective, I guess to try and compare the scope of this, let's compare four reactions. Let's say we look at the nitration of benzene versus the positional nitration of chlorobenzene, right? So what happens when we try to get the incoming nitro group at either the ortho, meta, or para positions of our chlorobenzene? Well, okay, so nitration of benzene, we'd have like just a standard set energy for that, right? Now, the generally speaking, the nitration of chlorobenzene, okay, regardless of whether it's ortho, meta, or para, it's typically going to be at a higher energy than that for the nitration of benzene. Chlorine is a halogen. It's still electronegative. It withdraws electron density through induction, and therefore we're going to notice, what we notice for deactivating groups. We're going to have slower reactions. We're going to have lower yields, and that's because the activation energy for each of the nitrations of chlorobenzene being higher than that of the nitration of benzene. So I'm not actually going to draw it here, but basically, whatever you've got as the activation energy for the nitration of benzene, the next three reactions are all going to have a higher activation energy. However, if we are comparing the orthonitration of chlorobenzene versus the meta-nitration versus the para-nitration, you'll notice that the para and ortho nitrations will have a slightly lower activation energy compared to the meta nitration. They'd still be higher than the nitration of plain old benzene, but they'd be lower than that of meta, the nitration coming in at the meta position. Okay, and again, it's due to that extra resonance structure and that stabilization that arises from that. Okay, so let's summarize this. All right, let's look at different substituents on our benzene and ask ourselves, what category can we put this in, and what do all the different examples in these categories have in common, right? How can we look at a substituted benzene and immediately know what type of group is this? Is it an activating group or a deactivating group? And how is it activating or deactivating? Is it strongly deactivating? Is it moderately activating? Is it weakly activating? Let's go break this down to different categories. All right, so here we have strong activators. Now, notice what all of these have in common. We have an oxygen or nitrogen attached to that benzene ring, but notice that these oxygens and nitrogens have groups attached to them that don't really have anywhere else for those electrons to go, right? These electrons are not going, can't go towards this hydrogen or to these, or to this R group, and so they have to get pushed towards the ring, okay? And so basically those lone pairs can be used in an inductive effect, and therefore can push that electron density into the ring. Next up, we have moderate activators. Now, just like with strong activators, we have oxygens and nitrogens here with their lone pairs attached to our ring. But unlike the strong activators, we have a carbonyl next to those oxygens. Now, what this does is it does involve a little bit of sucking away of electron density, right? This carbonyl can be can have its these pi electrons pushed onto the oxygen, giving it a negative formal charge, and that would cause these electrons to not only go towards the ring, but they could also be pulled away from the ring in this way. And so due to that, this is a not as strong an activator as here, where those electrons have to only go towards the ring. Here they can also go towards that carbonyl. However, basically, we also have resonance structures where these electrons can kind of be involved in pushing that electron density, around. We basically have an extra resonance structure, and therefore we can stabilize that sigma complex a little bit more. Okay. Notice that we have our alkoxy group here. Normally, you'd think, okay, an alkoxy group would be up here, but I guess with the in terms of the actual results we see in practice, it looks like it's more moderate than strong activator. So something to keep in mind there. Finally, we have weak activating groups. With weak activators, they don't work through induction at all. We have alkyl groups, and they only work through hyperconjugation. So pretty straightforward there. Next, we have weak deactivators. So with our weak deactivators, we have our halogens. As we pointed out, they are deactivating because through inductive effects, they suck electron density towards them. But remember, those lone pairs are involved in resonance structures that involve pushing those electrons towards the ring, even though from an electronegativity standpoint, it kind of works against it. So that's why we have that kind of sort of juxtaposition there, I guess. You have an ortho paradirector like all the other activating groups, but it's deactivating, and due to that electronegativity and that inductive effect. But again, that's what makes it a weak deactivator, okay? Because you have that countering effect from those lone pairs getting involved in the resonance structures. Then we've got moderate deactivators. Now, what do all of these have in common? All of them involve something, essentially you have some sort of carbonyl or carbonyl equivalent where that non-oxygen atom, so in most cases a carbon, or in this case a sulfur, are attached to the ring directly. So you don't have a lone pair on these atoms. That's the key thing. Unlike the moderate activating groups, where at least you had an oxygen or nitrogen that had a lone pair on it that could be pushed towards the ring, here there's nothing that pushes electron density towards the ring. Instead, that carbonyl, like with a moderate activator, sucks electron density away, but it only sucks electron density away. Okay, so through an inductive effect, those electrons get pulled towards the oxygens here, or in this case the nitrogen, in the case of this nitrile group, and that pulls electron density away from the ring through resonance. Okay, and then finally we have strong deactivators. Again, we just have multiple electronegative elements, so we either have multiple oxygens on this nitrogen, which put a formal positive charge on that nitrogen, or we have multiple halogens here, again very electronegative, really putting a positive, a partial positive charge on that carbon, or in this case here with with an ammonium ion, we have a formal positive charge on that nitrogen. Again, having that positive charge on that ring is definitely going to suck electron density away from the ring, trying to sort of counteract that positive charge. Okay, and that's what makes these groups strong deactivators. So again, noticing these patterns in these different groups will help you on a quiz or exam. In general, if you're looking at a molecule, ask yourself, which category does this substituent fit into? And so therefore, do I have, when you're trying to think, first of all, is this an activating or deactivating group? Is this going to be ortho paradirecting, or is it going to be meta-directing? And of course, remember, halogens are the exception there. And then, of course, look at the scope of that, or the strength of that activating or deactivating group. Okay, because that'll affect things like reaction rate and yield. Okay, so if you have a strong activating group, not only is it going to be ortho-paradirecting, but it'll also have a high yield. It might be a very reaction with a very fast rate, and therefore might be hard to control polysubstitution. Those are things to keep in mind. Okay, so like I said, basically look at your group, look if it's determine if it's activating or deactivating. Is your group electron withdrawing, electron donating? And then accordingly, if it's electron donating, it's probably an activating group. If it's withdrawing, it's deactivating. And of course, like I said, look at the strength of it. Okay, and then use that to determine whether it's going to be ortho, meta, paradirecting. All right, so let's practice that. Have a look at this molecule here and ask yourself, what type of group is this? Is it is it an activating or deactivating group? Is it ortho, meta, paradirecting, ortho, para, or meta directing rather? And is it going to be strongly activating or strongly deactivating? Okay. So if you've taken a second to think about this, you probably realize, hopefully, that this nitrogen has lone pairs on it. Okay, so we know that those lone pairs are going to get involved in being pushed towards that ring. So this is probably going to be an activating group. However, notice that carbonyl right next to it. Okay, so it's not going to be a strongly activating group, but it's probably going to be a moderate activator. Okay, but as an activating group, it's going to be ortho-para-directing. Now, notice that this group is relatively bulky, so there's probably going to be a preference for that para direction rather than the ortho direction. But there's going to be some steric hindrance here. Okay, so here, and of course, this you can rotate around this carbon-nitrogen bond. There's going to be a little bit of a barrier to rotation due to one of the resonance structures having some double bond character here. But my point here is that this carbon over here, or this hydrogen as well, is going to be sterically hindered when this group swings around over here. So both these ortho positions, while electronically are favorable, might be sterically a little bit less favorable. All right, so now we've seen how one substituent directs a second substituent coming in. What do you do if you have two substituents on your benzene ring, right? How do you determine which one takes priority in determining the addition of the incoming third substituent? So look at this example here. We have a methyl group over here on top. Okay, that's an alkyl group, and we have a nitro group here on the bottom. Okay, now quickly looking at these types of groups, we know alkyl groups are activating, we know nitro groups are deactivating, all right? And so the methyl group is going to be ortho-para-directing, and the nitro group is going to be meta-directing. So the question is, where does the incoming bromine go? Now, first of all, these two groups need not necessarily work against each other. So what is ortho to your methyl group is actually meta from the nitro group's perspective, right? So your bromine is actually going to show up basically at this position over here or here, which is ortho to your methyl group. But notice that from the nitro group's perspective, this is the ortho position, and that's actually the meta position, which, remember, your nitro group's meta-directing, so that actually works out pretty well. Okay, so that's where that bromine shows up. It shows up at that position that's ortho to that methyl group or meta to that nitro group. Okay, now have a look at this one. This one's a little bit tougher. Here we have an alcohol group. All right, so again, think about the lone pairs on that hydrogen, and if you recall, this is going to be an activating group, right? Those lone pairs can be pushed towards that ring, and you have an inductive effect. And of course, as we established already, that alkyl group, that methyl group, is going to be an activating group as well. Now here we have a conflict, right? Because that alcohol group will want your incoming nitro group to show up at that ortho position, right? For the alkyl group, which is also activating, that nitro group would want to show up at that, the ortho position to that, but that position is meta to the alcohol group. Likewise, the ortho position to the alcohol group is meta from the alkyl group's perspective, right? So which one takes priority? Well, this is why we wanted to categorize our groups into strong activators, or strong deactivators, or moderate or weak, because that is kind of what we use as our tiebreaker there. So these are both activating groups, but you have to remember that an alkyl group is only weakly activating, whereas an alcohol group is a stronger activator, right? So as a result, this alcohol group is going to take priority. The nitro group is going to show up at the position that's ortho to that. Okay, and that is what we observe. Okay. Another consideration taken into account is sterics. Here we have two alkyl groups, so they're both weak activators. Which one takes priority? Well, while both groups want to get the nitro group ortho to it, it makes more sense to have it ortho to the smaller methyl group. Okay, there's less steric hindrance there. Okay, so it makes sense that this product over here on the left is the major product. This product over here is the minor product. Okay. Likewise here, with this one, we've got a, we have two groups, but they're no longer para to each other. So what's ortho to both of them? Well, we have an ortho position here, we have an ortho position here, and technically there's another ortho position between the two of them. Well, that one's flat out, right? There you've got steric hindrance with both groups. Here you have steric hindrance with this bulkier group. So it makes sense that having the nitro group over here at this position that's ortho to this methyl group and para to the larger, bulkier group is your major product. Okay, whereas over here on the other side it's the minor product. Okay, so with that in mind, you want to consider how can we force groups to go where we want them to, right? So sometimes we want an incoming substituent to show up in a position that might not be immediately obvious or might not be, immediately feasible, right? So if we look at this bulky tert-butyl group here, we know that that's going to be ortho-para directing, but it's going to prefer to have a group be para, right? Because we've got this bulky group, that para position is going to be much more favorable than those ortho positions. However, we can see here that we're trying to put this bromine at the ortho position. So the question is, how do we do that, right? How do we force that bromine to go to that ortho position instead of the more favorable para position? Okay, and the answer is blocking groups. We want to block off that para position so that the bromine has no choice but to go to the ortho position. Once the bromine's been added, we remove our blocking group and we now have the product we want. All right, so you remember earlier, when we were looking at the different types of reactions, and I pointed out that when we sulfonate a benzene, right, we add on that sulfonic acid group. We do that by using concentrated sulfuric acid with sulfur trioxide, also known as fuming sulfuric acid. I pointed out back then that it's possible to reverse this reaction using dilute sulfuric acid. So we have a lot of water present. We can actually do the reverse reaction and remove that sulfonic acid group. Well, here's where that is really useful, because that is a great example of a blocking group. We can use that sulfonic acid to block off a site, and then once we have added on the substituents we want, we can remove that sulfonic acid group and we have the product we want. So that's actually what happens here. So we use fuming sulfuric acid to block off that para position with a sulfonic acid group. We then do our bromination, so we use bromine and our iron 3 bromide, and of course that puts the bromine over at the at that ortho position, because there's no para position for it to take up. It has to go to that ortho position. And then once we've done that, we use dilute sulfuric acid to get rid of that, of our sulfonic acid group. Okay, so to summarize all of the reactions we've looked at, okay, so this is probably a great slide to reference when you're studying the different reactions in this chapter. Basically, starting off at a benzene, we can do our EAS reactions. We can swap out a hydrogen for a particular functional group. If we want a halogen like a bromine, we can use bromine and iron 3 bromide or aluminium bromide. And if we want chlorine, we can do the same thing using aluminium chloride. If we want to do add a nitro group here, we can use nitric acid and sulfuric acid. For a sulfonic acid group, use fuming sulfuric acid. Then we have the Friel-Crafts reactions, right? So if we have a Lewis acid like aluminium chloride, we can then use an alkyl halide or an acid chloride, also known as an acyl chloride, to add an alkyl or acyl group respectively. Okay. Now, with that in mind, of course, there are further steps. Remember, if we want an amine, we can take a nitro group and reduce it by using iron or zinc and HCl. If we have an acyl group and we want to have the corresponding primary alkyl halide, a primary alkyl substituent, we can do a Clemmensen reduction using amalgamated zinc, hydrochloric acid, and heat it up together. Okay, so again, please note that this is the only way to get a primary, alkyl group, other than of course a methyl group. Um, because you can't do this directly from a Friedel-Crafts alkylation. And then, of course, if you think back to the last chapter, once you have an alkyl group in place, that benzylic carbon is pretty reactive, and of course, we can do, radical reactions at that, at that location. All right, we can use bromine or NBS to brominate that location, or we can use an oxidizing agent like potassium permanganate or sodium dichromate to convert that into a carboxylic acid. Okay, so with that in mind, you have to think about not only the functional groups you want, but also their directing effects. Okay, and as I pointed out earlier in this chapter, order of operations here is kind of important because of those directing effects, and also considering whether you have an activating or deactivating group. Okay, so let's look at 3-nitrobromobenzene. So that tells us that the bromine is in the number 1 position, and the nitro group is going to be meta to that. Okay. Likewise, we have another example here of 3-chloroaniline. Okay, so that means we have an amino group at the number 1 position, and we have a chlorine in number 3 position. Okay, so both of these steps might not be very straightforward. Okay, in the case of a bromine and the nitro group, which one do we add on first? You might be tempted to say we add on the bromine first because it's listed as being at the number 1 position in the way the name's written out. But remember, bromine as a halogen is orthoparadirecting. I've just established that nitro group is meta to that bromine. So it doesn't make sense to have the bromine on first. However, nitro groups, of course, are meta-directing. So this tells us we should do our nitration first, add on our nitro group, and then do our halogenation. Okay. This one is going to be interesting because if you have your amino group on first, again, that is also orthoparadirecting, right? And we want this chlorine at the meta position. Okay, so you've got to think back to how your amine is added on. Remember, it's not added on directly, right? You've got to first make a nitro group, put on a nitro group, and then you reduce that into an amine. And that is the trick to doing this one. Remember, your nitro group is meta-directing. So what you actually do is you first put on your nitro group, then you add your chlorine at the meta position, and then you reduce that that nitro group into an amine, okay, and turn it into an aniline. Okay, so to summarize those directing effects, we've got this slide here. So again, this might be another useful one to have on hand. I mean, you can derive all this stuff just by knowing all the other other reactions and their directing effects. But this is kind of a little sort of study guide, I guess, in a way, a little shortcut sheet to thinking about how do I want to get, how do I switch up the directing effects of something. Okay, so again, notice that here we have a nitro group that has our, that's a meta director, but if we reduce that to an amine, now we have an orthopara-director. Here we have an alkyl group, which is an orthopara-director. Of course, if we oxidize that into a carboxylic acid, which is a deactivating group, now we have a meta-director. Okay, and of course, if we have an acyl group, we can reduce that doing a Clemmensen reduction to an alkyl group. Again, that changes from being a meta-director to an orthopara-director. And finally, remember, if we have a lot of halogens on that benzylic position, now this is a very strong deactivator. So even though an alkyl group is an orthopara-director, the resulting halogenated alkyl group is a meta-director. Okay, Now, that being said, there are some limitations you should consider when you're designing syntheses. Okay, something to watch out for with nitration. Remember, you're using concentrated nitric and sulfuric acid. Those are very reactive reagents, and you want to consider that if you have more sensitive substituents already on your benzene ring, they might not stay that way. They might not stay those substituents if you try to do a nitration. Okay, so in this case, for example, here, you have an amine, and if you do this under nitric and sulfuric acid conditions, concentrated nitric acid is a strong oxidizing agent. You might oxidize this amine, and it won't stay an amine. Okay, so you don't get this nice para nitro complex or nitro product. Sorry. All right, Friedel-Crafts. Remember, one of the key requirements for Friedel-Crafts reaction is that you need an activating group, and having a deactivating group might prevent the reaction from happening. So, in both these examples here, we have moderate to strong deactivating groups, and therefore, we actually don't see a reaction occurring for this Friedel-Crafts alkylation. Okay, so with that in mind, let's try a practice problem here. So go ahead and see if you can synthesize this dibenzoic acid. Notice that the benzoic acids are ortho to each other. Okay, so if you had paused this and tried this out, you probably realize there are a few issues here. One, our carboxylic acids are meta-directors, so it seems unlikely that we have ortho-para directors, or that we'd have both these groups ortho to each other. Secondly, the bulkiness of those carboxylic acids would prevent you from having the group come in at an ortho position, even if it were ortho-para directing, right? It makes sense that you'd first add that second substituent to the para position as opposed to the ortho position. So those are two considerations to keep in mind when you're doing this reaction. So how do we get around that? Well, first of all, you don't want to add on your second group once you've already got a carboxylic acid. You need it to be something that's ortho-para directing. Okay, and so in this example, though, it is we're going to start off with an alkyl group. So we do a Friedel-Crafts alkylation. All right, and so we get we basically get a methyl group on here. It really doesn't matter which alkyl group we have. You could use any alkyl group here because we're going to react to that benzylic position regardless. The only caveat here is you have to have a proton on that benzylic carbon. So you can't use a tert-butyl chloride, for example. Okay, so here we're using methyl chloride. It's probably the most efficient way to do it. Any carbons beyond that are kind of wasted. So we do that twice. We have two equivalents of it. So we're going to add two methyl groups onto this benzene. All right, and then of course we can oxidize them to carboxylic acids using a strong oxidizing agent like potassium permanganate. Now, one issue that this synthesis that this answer slide has addressed is that we have both of our alkyl groups ortho to each other. We don't have another one here that's para. If anything, I would have thought the para product would be more likely, right? Even though methyl groups are relatively tiny, it still makes sense that you would probably get substitution at that para position. Okay, so something to consider then is that you may want to use a blocking group here, like sulfonic acid, to block off that para position. Then add on your second alkyl group at the ortho position, and then remove that accordingly. All right, let's try another one here. So this one's a little bit tougher. We've got 3 substituents, and we don't know we want to kind of work backwards here. That's probably the best way to kind of figure things out. Instead of starting from benzene and thinking like, okay, what order should I add these things in? It might be useful to think backwards and think, which one did I add last? All right. So, by the way, just to jog your memories, remember this is a retrosynthetic arrow. I think we first introduced this last semester, but this means that you're working through the synthesis backwards. Okay, so this arrow, instead of saying like, oh, this is your reactant and this is your product, what this is implying is that this is the product. It came from what reactant? Okay, so you're going backwards a step. Okay, so with that in mind, what is the last group attached here? So a big hint here would be the how activating, or rather how deactivating, our groups are. Now, all three of our groups are deactivating groups, actually. You have your bromine, which is a weak deactivator. You have your acyl group over here on the right, which is a moderate deactivator. But most importantly, we have our nitro group here, which is a strong deactivator. So that actually would probably be the last group attached, because remember, here we've got an acyl group, which we add on through a Friedel-Crafts acylation, and in order for that to occur, you need an electron-rich ring. It's kind of difficult to do that with a nitro group on there. Okay, so that's probably the last thing we add on. All right, so this is probably what we've got right there. Okay, it makes sense that we don't have the nitro group on here and try to add one of the other groups later, because that nitro group would interfere with that, right? It's too deactivating. Okay, now let's keep working backwards. What can, out of these two groups, which one must have been added on, in the previous step? Well, here you might want to consider the directing effects to each other, right? We have bromine, which, even though it's deactivating, is ortho-para-directing, right? And here we have an acyl group, which is meta-directing. Okay, now notice that these groups are para to each other, so that should tell you then that the bromine couldn't have been added last, because if it were added last, it would have been in the meta position. So it must be that acyl group that was added in the previous step. Sorry, I didn't mean the bromine was added last. I mean, like, in the, if we add a retrosynthetic arrow over here, we don't, we should have bromine on the reactant that this product comes from. Okay, so I guess I kind of, basically, show that here. So if we go from, if we were to write out all our first steps forwards, from benzene onwards, our first step would be to add that bromine. Okay, so we do that through our regular bromination. So you use bromine and aluminum bromide or iron 3 bromide. Then we add on our acyl group. So we have an acyl chloride here with aluminum chloride. We do a Friedel-Crafts acylation. Okay, and there we get that intermediate. And then in the last step, we add, using concentrated nitric and sulfuric acid, we add our nitro group. And it's going to show up here at this position that is meta to our acyl group, which is where it wants to be, and ortho to our bromine, which is also, again, where it wants to be. So you can see how we're kind of forced towards this route, right? We have to basically follow these steps. I know we have the reagents we need to put the substituents we want, but we have to go in this order in order to have the substitutions show up where we want them. So that's one of the trickier things with a lot of these EAS reactions. Not only do you have to consider the substituents, the functional groups you're adding on, you also have to consider the directing effects off those functional groups. Okay, and that affects what order you do your steps in. Okay, so we've talked a lot about EAS reactions in this chapter. However, there are two other reactions that we want to look at. One of them is nucleophilic aromatic substitution. The other is elimination addition reaction. So let's first look at nucleophilic aromatic substitution. In this reaction, we basically substitute out our one of our substituents, notice that here we're using a nucleophile to do this reaction. So this is kind of weird, right? We have, in all the other examples, we've dealt with electrophiles, things that had either a formal or really strongly partial positive charge. Here we have a hydroxide ion with a negative formal charge, and that's what the group that we're swapping in for. Okay, so that's really interesting. You've got to think about the difference here. How can we do this reaction given what we've seen with nucleophilic, the nucleophilicity of our benzene ring, the electron-rich nature of that. Okay, so in order to do this, there are three things you need to, basically to have a nucleophile work together with your nucleophilic benzene rather than an electrophile, as we've seen in EAS reactions. First, of course, you must make the ring electron poor. Okay, in order to, if you have a lot of electron density in that benzene, it's not prone for a nucleophile to attack it, right? So how do we do that? Well, we swap it out, or we substitute a really deactivating, a very strong electron withdrawing group on the ring. I don't know if I go back a slide, I don't know if you guys noticed that we had a nitro group present on the ring. Okay, so that's kind of key for doing this reaction. All right, if that nitro group were not there, this reaction would not occur. Okay, you must have a good leaving group. All right, so notice that in that reaction, the the alcohol that we add on substitutes not a hydrogen as we saw in EAS reactions, but instead we're swapping out that bromine. Right, so we have bromine there as our leaving group. We need we need a leaving group like that present for the incoming nucleophile to swap out. Okay, finally, those two groups, so the first two requirements we have here involve substituents that should be on our benzene ring. The third requirement is a directional one. We need these two groups to be either ortho or para to each other. Now, why is this? We're going to see in the mechanism, basically look at the intermediates and look at the charges on those intermediates. Okay, so if we start off with our reactant, okay, so we have our two, our two required groups. We have our electron withdrawing nitro group. We have our leaving group. In this example, it's a chlorine. So, and we have them para to each other, right? We start off with our nucleophilic attack. So we have a nucleophile comes in, and we have it attacking the site where our leaving group's attached, because eventually we want that to leave. Now, the intermediate we make is called a Meisenheimer complex. Okay, so like a sigma complex, except instead of a positive charge being spread around through resonance, we have a negative charge here. Okay, which again makes sense because we have the nucleophilic attack arrow going this way towards the benzene ring and not to an electrophile like we see in EAS reactions. All right, so we have our Meisenheimer complex. Now think about the resonance that we're going to see in that Meisenheimer complex. Okay, so draw all the resonance contributors for this. Okay, so here's what that looks like, right? We start off with that negative formal charge over here in the top left. We have it move down here. It can move over here, and it can also move down to that nitro group. Okay, so again, it's very useful to have that nitro group at that position where it can be involved in that resonance. All right, if that nitro group were in the meta position, the negative formal charge, that lone pair would skip over it to this para position here. Okay, onto the other, and skip over the other meta position onto the ortho position here. So basically, we need that nitro group to be either ortho or para. Okay. All right. So that's how that Meisenheimer complex is stabilized, of course, and therefore that lowers the transition, the potential energy of that transition state, making that pathway more likely. Finally, we have our leaving group leave, and when it leaves, it reestablishes aromaticity to that benzene ring. Okay, so we lose our leaving group, and now we have our alcohol group there instead of that chlorine. Okay. So that's kind of what we observe. We see that nitro group, where in the meta position, our Meisen hybrid complex would be less stable. Okay, and so as a result, there's no reaction. Okay. Something that might help to drive the reaction forward is having excess of your nucleophile. But keep in mind that sodium hydroxide, in addition to hydroxide being a nucleophile, it's also a base, right? So in this case, since we're putting on an alcohol group and we're making a phenol, remember phenols are pretty acidic, so we would wind up with the deprotonated version. And that's why the second step of the reaction involves adding an acid, and that's how we get the protonated version accordingly. So as I pointed out earlier, having a electron withdrawing group is kind of important for nucleophilic aromatic substitution. You need, in order to make that ring electron poor enough so that a nucleophile will attack it, you need something to pull that electron density away from it. That being said, while you wouldn't expect a benzene without that electron withdrawing group to undergo an NAS reaction, it is possible to get it to undergo a reaction overall using harsher conditions. Notice that instead of just having this warm at 70 degrees Celsius, moderately hot, I should say, at 70 degrees Celsius, we have a really high temperature here of 350 degrees Celsius. And so having those harsher conditions does drive this reaction forward and makes that, we swap out that chlorine for that alcohol group. Okay, so how does that happen? Okay. By the way, it also helps to have a really strong nucleophile in this situation. So, for example, instead of hydroxide, here we've got an amide ion, which is very, very nucleophilic, right? Very, very basic as well. Really reactive, and so that's why we see this reaction, this substitution. Now, that being said, all right, we don't see one product when we have multiple substituents. So over here with just the benzene and that leaving group, it doesn't really matter, where the amine goes. Like, you only have one product. But if you try this with toluene, where now there's already a methyl group sticking out there, we observe that there's actually two products that we get. All right, so we see that nitro group where the chlorine was, but we also see the, not nitro, that amino group showing up where the chlorine was, but we also see that amino group where, on a carbon adjacent to that, okay, where that leaving group used to be. Okay, so why is that? We can't have it go through our NAS mechanism, right? This doesn't account for why we would see this second product, so it must be another mechanism involved. So if you want to study this mechanism, one way to go about it is to do a labeling experiment. So essentially what you do is you pick a relevant atom and you swap it out for a different isotope, one that you can either pick up using a mass spec or probably an NMR, or it might disappear in NMR. And so we basically can identify where that atom is in our products, and that gives us a little insight into the mechanism that led to that product. So if we do a labeling experiment, let's say we label the carbon where our leaving group's attached with a carbon 14 instead. Okay, basically we'll see that carbon, in our products we have that amine attaching to that carbon, but we also have it at an adjacent carbon. Okay, so it kind of proves again that we can't be going through that NAS reaction, but it does tell us that essentially what's going on is that these two carbons, these two positions must be equivalent somehow. So what happens is that we must be going through what's called a benzyne intermediate. We have an intermediate that basically has a triple bond. Okay, so what's happening, instead of our our nucleophile coming in, adding on, and then our leaving group leaving, is that we actually have essentially an elimination reaction, right? We have our nucleophile actually acting as a base here. It deprotonates that position next to where our leaving group is, and winds up eliminating the hydrohalogen there. So we have our leaving group leave, we have hydrogen leave, and we basically form another pi bond here. Now, just looking at this looks kind of problematic, right? Because think about what you know about alkynes, right? And what you know about sp hybridized carbons. They like to be linear, right? This is very not linear, so that looks really, really weird. Okay, and that tells us automatically that this benzyne's probably not very stable and therefore pretty reactive, and it's probably going to react relatively readily to make our products. Okay, if you want to understand why, again, those sp hybridized orbitals can't really overlap very well, and so we essentially have them kind of sticking out. It's almost like a diradical. Okay. All right, so that being said, it's prone to an attack. That nucleophile, we've got the strong nucleophile readily available to attack that very reactive benzyne, and so it doesn't really care which carbon it attacks. It can attack either one, either the isotopically labeled one or an adjacent carbon, right, where we have the other end of that triple bond. Okay, and that's how we get our two different products. Okay, so we basically have our nucleophile attack our alkyne. We result in this resulting anion, which then gets protonated to make the resulting product. Okay. Oh, by the way, please note that we had we used an amine, amide ion rather, twice in this reaction. First, we used it as a base. Secondly, we used it as a nucleophile. All right, so even though we have ammonia acting as our acid in this case, please note that we had to use two equivalents of our amide ion to get and only get one back. So amide's not being regenerated. It's acting as it's not acting as a catalyst here. All right. Another piece of evidence to show that we're going through a benzyne intermediate is, remember, these benzynes are really reactive. They readily will undergo a Diels-Alder reaction. All right, so it's a really strong dienophile here. So if you have a a diene readily available, so here we have furan, for example, note that we have the resulting cycloaddition product. Okay, so how do you figure out what's going on with these three options? We have our electrophilic aromatic substitution, we have nucleophilic aromatic substitution, and then, as we just saw, we have an elimination addition reaction. Okay, and oftentimes we have very similar reagents, right? Especially in the case of our nucleophilic aromatic substitution and elimination addition, right? We have really strong nucleophiles there. How do we distinguish between these? Okay, so first of all, look at your reagents and ask yourself, am I using an electrophile or a nucleophile to do this reaction? It sounds like a dumb question, but that's obviously the big difference between an electrophilic aromatic substitution and these other two, which require nucleophiles. To distinguish between those last two reactions, of course, remember, nucleophilic aromatic substitution had three key requirements. You need all three of those requirements to be met for it to be a nucleophilic aromatic substitution. If you don't meet all those three requirements, for example, if you don't have that strongly deactivating group present, you're going to go through this alternate mechanism. You're going to go through do an elimination addition instead. All right, and that's it for this chapter. So let's go through these practice problems. But again, as always, I do recommend trying the suggested problems that I've put up on Blackboard. All right, so here we have a benzene, and they've given us our reagents. Let's figure out what the product's going to be. So looking at our reagents, we have a tertbutyl chloride and an aluminum chloride. Right, so aluminum chloride here is going to act as a catalyst / Lewis acid catalyst. What type of reaction do these reagents, yield? Okay, so here we have a setup for a Friedel-Crafts alkylation. Right, this is the alkyl group we're going to add on, and so here's the complete mechanism. Basically, it reacts with our aluminum chloride, produces this complex, which essentially plucks off the chlorine and produces a stable carbocation. Okay, it's possible for our benzene to react directly with this, but effectively it might be easier to show this as a separate carbocation. Our benzene attacks that, and you then have our sigma complex. Of course, this is resonance stabilized. We're only showing the one complex. We're not showing all the resonance structures. And then of course we have our complex. Which can also act as a base, and so it plucks off that extra proton, restoring aromaticity, and there we have our alkyl benzene as the product. Okay, here we have what looks like two near identical reactions, right? So both of these are going to be nitrations, right? We've got concentrated nitric and sulfuric acid. We're going to basically add a nitro group. The question now becomes, what is the directing effect of these groups? Okay, so while these groups, the substituent on these two molecules has all the same pieces, notice the connectivity is a little different, right? So here we have a nitrogen connected to a carbonyl connected to an alkyl group. Here we have the carbonyl connected to the nitrogen connected to the alkyl group. So here we have the nitrogen connecting to the benzene ring. Here we have the carbonyl connected to the benzene ring. Okay, so ask yourself, are these activating or deactivating groups? Are they going to be ortho-para-directing, or are they going to be meta-directing? Okay, so as soon as you see this nitrogen with its lone pair attached, you should realize, okay, this is going to be an activating group. It's going to be an ortho-para-director. Now, given the bulkiness of this group, I would say the para position is going to be favored. All right. Now here we have a carbonyl, which again should make you think deactivating group, and that's the case. It's going to be a meta director. So here you can see the nitro group shows up at the para position. Here it shows up at the meta position. All right, here we have a multi-step synthesis. This one's going to be a little bit tougher. It takes you back to some concepts from last semester. And so this one's going to take quite a few steps to kind of bring things together. Okay, it might be easier to actually do this retrosynthetically. We look at this product and ask ourselves, okay, how do we get these together, right? So you want to consider, basically where is a good site for this to form. Now here, notice that we have an alcohol group and we have another, and we have carbons attached to that alpha carbon. I will point out a very useful reaction here to do the setup might be a Grignard reaction, right? So if this used to be a carbonyl, it might be relatively easy to have an R group, a Grignard reagent attack that carbonyl, right? Depending on which way you do this. So that's just an option. So pause this video and see if you can think of any particular ways to go about this. Okay. All right. So looking at the answer here, right, you can see that we do have two sort of pathways leading to our Grignard reaction. So here we're making our Grignard reagent. Over here we're making the carbonyl that the Grignard attacks. Okay, so both of them start off with a benzene. Now here we eventually want our Grignard to be para to that alkyl group. Now, the problem with the alkyl group that's on there is that it's a primary alkyl group, and we've seen that we can't do a Friedel-Crafts alkylation with a primary alkyl halide. So you actually first have to do an acylation and then do the Clemmensen reduction to get the resulting alkyl group there. Now, that alkyl group is going to be ortho-para directing. It's a pretty bulky group, so it makes sense that you're going to get your other substituent para to it. Remember, to make a Grignard reagent, you've got to take an alkyl halide and then react it with magnesium and ether. So we need, if we're doing this retrosynthetically, if we want to make this Grignard reagent, we have to have a bromine at this position. Okay, so that's why the step over here involves taking that alkyl benzene and then doing a bromination with it before we then convert to a Grignard reagent. Okay, over here we can see that we are effectively doing an acylation. Our acyl group here just only has a hydrogen as its R group. Okay, and now we have our Grignard reagent, which, remember, this carbon that our magnesium is attached to, that's going to be where our nucleophile is. That's effectively a carb anion. So that carbon is going to connect to this carbonyl carbon, making this intermediate, which we can then protonate to make the final product. All right. So, and again, don't panic. That was a very long, complicated reaction, a very long, complicated example. Hopefully you won't see anything that ridiculous on a quiz or exam. Okay, so here's another multi-step synthesis problem, except here they're giving you the intermediates and they want you to fill in the reagents. Okay, so for each of these steps, look at the reactant it comes from, look at the product, and ask yourself, what reagents do I need? Now, please note that in some cases we have multiple substituents added on, in each step, so you may have multiple reagents, multiple reactions going on in a given step. Okay, and you might also want to consider order of operations, right? Because you've got to consider the directing effect of those substituents. So again, pause this video and see if you can figure out what reagents go into these 5 blanks. Okay, so if you've joined us back, here are the answers. All right, so notice that over here, to make this product, we have a bromine and we have an alkyl group. Okay. These are both, ortho-para directing, but so it kind of seems kind of weird that they're meta to each other, right? So that tells us that they probably weren't in this form when this happened. So how do we get this primary alkyl group on here? Now, again, we know that goes through an acyl intermediate that we can then reduce down to the primary alkyl group. Well, that acyl group is going to be meta-directing. So it makes sense that the first step is to add on that acyl group. So we do a Friedel-Crafts acylation, okay, with the necessary alkyl group on our acyl chloride to show up here. We then add on our bromine, okay, using our bromine and either our iron 3 bromide or aluminium bromide. And it's only then that we reduce our acyl group down to this alkyl group. Okay, so the order in which we do this is very, very important. If you switch up the order for this, you would, immediately make an isomer of this that is not the product you want. Okay, so now for reaction B, the difference between this chemical and this chemical is that we have oxidized that benzylic position to carboxylic acid, which, if you recall, we can do that with a strong oxidizing agent like potassium permanganate. All right, now looking at this reaction, the difference here is we are adding on a nitric group. So again, the reagent for that is concentrated nitric and sulfuric acid. So that one's pretty straightforward. If you want to confirm the directing effects, you want to make sure you remember that this is ortho-para directing, this is ortho-para directing as well, even though it's deactivating. So it makes sense that the 2 sites that are very likely, so basically you could either have, this position, or this position are all, ortho and or para to those groups. out of those, it makes sense that the nitro group shows up over here. You definitely don't want it over here where it's in between those two bulky groups. And out of these two ortho positions, while the bromine is pretty bulky, it's smaller than this propyl group. So it makes sense that the nitro group is ortho to it. Okay. So when we look at the reaction here to make D, the difference between these two molecules is that our nitro group's been reduced into an amine. So remember, you can do that with zinc or iron and HCl. So it looks like here they're using zinc, but you could have used iron if you use that. That's still correct. And over here, this one's interesting. We have our bromine swapped out for an ethoxide group. Now, you probably say to yourself, like, wait a minute, I don't remember an EAS reaction that does this. And that tells us that this is probably not an EAS reaction. This, ethoxide is a nucleophile, right? So we could use sodium ethoxide here as our nucleophile. We do have a nitro group. Okay, so notice that this molecule meets all three requirements for our nucleophilic aromatic substitution. We have a strongly deactivating nitro group, and it is, we have a good leaving group here in this bromine, and notice that the nitro group is ortho to the bromine. Okay, remember, we need those two groups to be either ortho or para to each other. And in this case, they're ortho. This meets the requirements for an NAS reaction, and that's what happens. We swap out the bromine leaving group for our ethoxide. So again, we need to have our ethoxide in a nucleophilic form here. So we use sodium ethoxide as our nucleophile. Okay, as opposed to, like, let's say ethanol, which would be which is only weakly nucleophilic. All right, that's it for this chapter. So as always, let me know if you have any questions. Please do try out these practice problems. You can see, especially, this chapter is very synthesis heavy, and this stuff really comes together with practice. It's very procedural stuff. So be sure to try out the homework. All right. Good luck with your quiz, and we'll catch you in the next chapter.